in today's video, we're going to be looking at the introduction to waves physics. We will talk about the different types of waves, and we'll examine the mathematical relationship between the frequency, wavelength, period, and velocity of waves. Now, let's say we have a pool of water, something like this, and then we drop a stone, a tiny stone, just at the center of this pool. What happens is that this stone will cause ripples moving in circular manners like this. Alright, so we have a ripple effect when a stone is being dropped inside the water. Let's also say we have a cord that is clamped at one end. Now let's say we flip this other end. You're going to have something like this in form of a wave, and then it continues like this. So if you flip, if you have a cord that is tied at one end, and then when you flip the other end, you have the cord making this sort of wave. Now what is happening is actually a transfer of energy. What is happening is actually a transfer of energy. Same thing as when we had a stone being dropped into a pool of water, there's a ripple effect. That ripple effect simply means a transfer of energy, and this energy is as a result of what is called wave. Now, what is wave? Waves can simply be defined as a process of transferring a disturbance in the form of kinetic energy from one point to another in a medium without any transfer of the particles of the medium. So that explains the reason why if you have a leaf on a pond and then you drop a stone and this ripple effect takes place, that leaf is not moving, rather the leaf moves up and down but does not change position. Only the wave motion changes position. So what happens is there's a disturbance as a result of wave motion, and this disturbance causes a kinetic energy transfer between one point of the medium, and the medium in this case could be a river or a pond. The medium can also be a string or a cord as explained here. So kinetic energy is being transferred from one form of the medium to another, but there's a limited movement of the medium and every other particle that is within that medium. Now, there are basically two types of wave motion. We have the mechanical wave and we have the electromagnetic wave. Mechanical waves are those waves that require material medium for their propagation. For instance, the wave on a cord, as explained here, is a mechanical wave. The wave on a water or on a pond is a mechanical wave. Why? Because we need a pond to carry out or investigate this wave. We need a cord to investigate this wave. So any wave that requires a material medium is simply called a mechanical wave. So examples of such waves are, like I said, water waves, we have sound waves, we have waves on a rope or string. So sound waves as well. Take for instance your trumpet. You need to blow your trumpet before it can produce a sound. So take for example also your speakers. When you speak through your amplifier or through your mic, the speaker amplifies your voice. So these are good examples of mechanical waves. We also have electromagnetic waves. Now, electromagnetic waves are simply those waves which do not require material medium for their propagation. Examples are light waves, radio waves, X-rays, and gamma rays. Now, it is important for you to know that we can actually classify wave motion based on the vibrating particles with respect to the direction of travel of the wave. Now, considering this, we have two types of wave or two classes of waves. We have the transverse wave and we have the longitudinal wave. Now, transverse waves are waves which travel perpendicular to the direction of the vibrations producing the waves. Now, I give an example. Considering the cord which we used earlier for our introduction, this can also be called a string. Now, this is a good example of a transverse wave, waves on a curve. So I have the direction of wave which is in this manner. Now this wave can come down here and then move again up, and then come down and then move again up. So you can see that the vibration producing the wave is from where? This end. This is where the wave is being produced when we flipped this end, and then we have the direction of wave in this manner. Now let's call this direction x. So it means that the wave motion is also moving here in the horizontal direction or towards the direction of x. Meanwhile, the point where we flipped the cord was just directly by this point. So this point is purely vertical where we flipped this point. So you see that this point is vertical, but the direction of motion of the wave is what? Horizontal. So you have something like this, vertical, and then you have horizontal, and these two are perpendicular to one another. So if the direction of the motion of the wave is perpendicular to the vibration causing the wave, then we simply have a transverse wave. So an example of a transverse wave is simply wave through a cord or through a rope or through a string. Now the second class of wave is the longitudinal wave. A longitudinal wave are waves which travel in a direction parallel to the vibration of the medium. Now a good example of longitudinal waves can be seen in springs. Okay, let me take this off. A good example of longitudinal waves can be seen in springs. So you have a spring, let's say we have a coil spring in this manner. Okay, now when we apply, let's say this spring is tied at this point, right? Now if we apply a force on this edge to cause vibration, if we apply a force on this edge to cause vibration, what happens to this spring? The spring will what? Compress to one another. So we'll have something like this. The spring will now become compressed to one another due to what? The force applied. So the spring becomes compressed. Now there's a wave motion taking place here. Of course there's a wave taking place because whenever a force is applied on a cord or on a spring, we are simply going to be having a waving motion. Okay, so you see now that the direction of wave, what is causing the wave is purely horizontal, and the direction of wave is also what? Horizontal. So the two of them are parallel to one another. The propagation, or what is propagating the wave, is purely what? Horizontal, and the direction of the wave is also horizontal. So which means these two waves are what? Parallel to one another. So a good example of a longitudinal wave is simply a wave on a spring, whereas a wave on a rope or string is a good example of a transverse wave. Now let's take a look at the transverse wave. Using this waveform shown here, let's explain some terms that can be used in waves. Now, taking a look at the nature of the transverse wave, we could be able to determine some terms which are being used in wave. Okay, so examining the transverse wave, we can be able to deduce some terms which are frequently used in waves physics. The first term there is the displacement, followed by the amplitude, followed by wavelength, followed by crest, followed by troughs. So the first term we are going to be talking about is a cycle. What is a cycle? A cycle is simply the complete to and fro movement of a wave or an oscillating object. A complete to and fro movement of an oscillating object or simply a wave. Next, we talk about the amplitude. Amplitude is simply the maximum displacement of an object from its position of rest. So this is the position of rest. The maximum displacement of that object from the position of rest is simply called amplitude. Okay? It's simply called amplitude, and it is symbolized by capital letter A. The next is called crest. Now, on examining the waveform, these highest points are called crest, whereas these lowest points are called troughs. The distance between two crests is called the wavelength. Similarly, the distance between two successive troughs is also called the wavelength. So distance between two successive crests or troughs is called the wavelength. And wavelength is symbolized by the symbol lambda. Now, another frequent term which we are going to be using in waves physics is the frequency. Frequency symbolized by F. The frequency is simply the number of complete revolution or oscillation which a particle makes in 1 second. The number of complete revolution or oscillation which a particle makes in 1 second. Mathematically, frequency is given simply as 1 all over period t. Mathematically, frequency is given as 1 all over period, and it is measured using the hertz. It is measured in hertz. Now, if frequency is 1 over period, it also means that period becomes what? 1 all over frequency. Now, period simply means the time it takes to make one complete revolution. The period t means the time it takes to make one complete revolution. Period t, and it is mathematically given as 1 all over frequency, measured in seconds. Now, another thing we can talk about is speed. Remember we said earlier that wave motion is simply a disturbance that transfers kinetic energy from one point of a wave to another point without a transfer of the medium or any particle on the medium. So we can't talk about kinetic energy without talking about wave speed. What then is a wave speed? The wave speed is simply the distance which the wave travels in 1 second. Okay, wave speed symbolized by V is the distance which the wave traveled in 1 second. Okay, per unit time. So this simply distance traveled by the wave per unit time. Now, the wave speed is simply what? Velocity. Now, the distance traveled by the wave or distance required to make one complete revolution is called wavelength. We said that earlier. The distance required to make one complete revolution is called wavelength. So this simply means that our distance here is our wavelength. So we simply have wavelength all over time. So this simply implies our wave speed is simply wavelength all over time. So from here, if you make wavelength subject of the formula, this means mathematically wavelength is simply what? The wave speed multiplied by time. So this is our equation for wavelength, keeping this aside. But you recall that we said period itself is actually 1 all over frequency. So if you plug that into this equation, you're going to now have that our wavelength is going to be equal to the wave speed multiplied by period, which is 1 all over frequency. So from here, you can find an alternate equation for the wave speed, V, to now be equal to what? Frequency multiplied by wavelength. So keeping these equations in mind, our wave speed is simply frequency multiplied by wavelength, and the unit is a meter per second. So it also means that from here, we can also find an alternate equation for our wavelength, which becomes velocity all over frequency, or the speed divided by frequency. So this can also be an alternate equation for our wavelength, okay? And the unit of wavelength is in meters. Wavelength is measured in meters, since it is simply what? A measure of length. Now, the next term on this graph is the displacement, y. As can be seen here, the displacement y. The displacement is simply the vertical distance accomplished by a wave. The vertical distance accomplished by a wave. And since we are talking about a wave, the displacement takes a waveform. Okay? Displacement is simply the vertical distance accomplished by a wave. And the displacement y is simply given as a sine 2 pi x all over lambda. So this is the equation for all wave forms. This is the equation for all waveforms. Now, and this equation can also be written alternatively as a sine 2 pi all over lambda multiplied by x in a bracket. Now there's a reason for this, because x simply talks about what? Displacement, horizontal displacement. So when you look at the graph once again, we introduce that the motion of the wave is purely what? Horizontal. So this is horizontal displacement x. All right. Now if you consider the motion of a wave at a given time t, then you have to recall that velocity is actually distance, or speed is distance all over time. So you can simply make distance subject, it becomes what? Velocity times time. So when you consider the motion of a wave at a given point in time, then that means our sine wave equation for displacement now becomes, this simply implies that our displacement becomes, we have a sine 2 pi all over lambda now into, I have the horizontal displacement x minus velocity times time, which is now the distance covered by the wave you're considering. Now you recall that we said earlier, that velocity is actually frequency multiplied by wavelength, which is lambda. So which means you can rewrite this equation simply as a sine 2 pi all over lambda multiplied by, we have x minus, in place of velocity, we have frequency times lambda multiplied by time t, and you have this. So this simply implies that y is now going to be equal to a sine, let's now expand the bracket using 2 pi over lambda. This becomes 2 pi x all over lambda minus, we have 2 pi multiplied by frequency times lambda times time divided by lambda. Okay, so this is going to be equal to a sine, we have 2 pi x all over lambda minus, over here lambda cancels lambda, we have simply 2 pi ft, and we close our bracket. So but you recall from circular motion, that omega is actually 2 pi f, which is the angular speed, which is the speed around a cycle. So this simply implies that our vertical displacement y is going to be equal to a sine, we have 2 pi x all over lambda minus, in place of 2 pi f, that is omega t, where omega is our angular velocity, t there is the time in seconds, and of course a represents the amplitude, which is the maximum vertical displacement, and then lambda is our wavelength, and x is the horizontal displacement. So all waveform takes this equation for the vertical displacement, a sine 2 pi x over lambda minus omega t. You could be asked different questions to actually solve comparing this equation. So right now we're going to be delving into solving some examples just to back up everything we have said. Now let's consider this question. It says the frequency of a vibrating source is 450 Hz and the velocity of the sound it produces in air is 330 meters per second. Question says find how far the sound travels when the source completed 50 vibrations. So let's pick out our parameters. The frequency of a vibrating source is 450, so we are given frequency. F was given as 450 Hz, and the velocity of the sound it produces in air, so velocity of sound V is actually 330 meters per second. Okay, so we are now to find how far the sound travels, that is distance. Okay, unknown, given number of 50 vibrations, so number of oscillation. Call that n is given simply as 50. Okay, so you recall, since you're asked to find distance, recall that velocity is actually distance all over time. So this simply means your distance becomes velocity times time. So we know the velocity, but we don't know the time for 50 vibrations. But you recall that period, which is t, is actually 1 all over frequency, and this is equal to 1 all over 450 hertz. So our period is going to be equal to 1 divided 450. So that simply gives us approximately 0.22 by 10 to the power of negative 3 seconds. Now, but for 50 vibration, this is period for one vibration, but for 50 vibrations, our period t becomes what? 0.22 by 10 to the power of negative 3 multiplied by 50. So this means that the time is going to be equal to 0.22 multiplied by 50. That gives us approximately 0.11 seconds. So we have 0.11 seconds. So this becomes our period. Now, since we know the velocity, we can easily find our distance, or distance of the sound traveled, simply velocity times time, and that time becomes our period. So velocity is 330, therefore distance s is equal to velocity is 330 multiply 0.11, and this is going to give us times 330. So we have approximately 36.67 meters. So you have 36.67 meters, and this becomes the distance traveled by the sound. Now one more question and we are done with this section. Now let's consider the second question. It says a plane progressive wave is represented by the equation y equals 2 sine 200 pi t minus 0.5x, where the symbols have their usual meanings. What is the frequency of the wave? So let's get down the equation given to us. We are given that y is equal to 2 sine 2000 pi t minus 0.5x, and we are asked to find frequency. Okay, now to solve this problem, you recall the wave equation. The wave equation is simply, recall, our wave equation y is equal to a sine, open bracket, we have 2 pi x all over lambda minus omega t. Okay, so we simply have this is our wave equation. So upon comparison, you're going to find out that, now just be careful, we have 2 sine 2000 pi t minus 0.5x, then you have a sine 2 pi x over lambda minus omega t. So this means the amplitude A stands for 2, where sine goes for sine, but be very careful, this is 2000 pi t, whereas what you have here is 2 pi x over lambda, and this is 0.5x. So which means comparing these two equations, 2 pi x over lambda goes for 0.5x, and of course omega t and omega t goes for 2000 ft, because as can be seen here, goes for 2000 pi t, because as can be seen here, t is the leading between these two equations. So we have t here and we have t here as well. Okay. So upon comparison, we are going to be having that 2000 pi t is going to be equal to omega t, but you recall that omega itself is actually 2 pi f. So if you put that into the equation, you're simply going to have that 2000 pi t is now going to be equal to, in place of omega is 2 pi f. So you put down your t. You observe that t cancels t from here, right? T cancels t from here. So this simply implies that 2000 pi is going to be equal to 2 pi f. Also, pi cancels pi as well. So this simply implies that 2f is actually 2000. So you can simply make the frequency subject. That becomes 2000 divided by 2, and this will simply give us 1000 hertz. So for that given question, the frequency is simply 1000 hertz. Alright guys, so that's it for this video. In the next video, we are going to be solving numerous of problems under waves physics, and then in subsequent videos we can look into the properties of physics, talking about interference, refraction, diffraction, and so on. I will see you in those videos. Thanks.